Now, in the last lecture, we pointed out that the major greenhouse effect in Venus is by carbon dioxide. The next important is clouds, because it is completely cloud covered, and thirdly, little amount of water vapor has a big effect. Okay. So, this is what makes Venus unique. Okay. The question is, what went wrong with Venus? Why did the Venus greenhouse effect become so strong? And the answer is, Venus climate got out of control because of the runaway greenhouse effect, because there was a lot of positive feedback loops when Venus became hot. Okay. So, these feedback loops are similar to what we discussed for Earth, but much stronger and much more effective. Okay. See, Venus had some ocean a long time back. There is no ocean now. Okay. Because it was closer to the sun, it was hotter beginning, and the higher temperature caused the water in the Venus to evaporate. And because the temperature was larger than on Earth, the water did not condense back. So, the ocean vanished. All the ocean in Venus just evaporated into the atmosphere. And once the temperature went above a certain value, then the rocks which had a lot of carbon dioxide, it also started having chemical reactions which released that calcium carbonate into carbon dioxide and calcium oxide. Okay. So, as the temperature goes very high, all of you know from the Arrhenius equation that the reaction rate of a chemical reaction depends on temperature exponentially. Okay. So, as the temperature goes up, the reaction rate will go up exponentially. Earth is at a cool 50 degrees centigrade, but in Venus, as the temperature went up to 100, 200 degrees centigrade, the reaction rate in Venus went up and the rock started chemical reaction which released calcium carbonate from the Venus surface into the atmosphere. Okay. So, once all the water vapor evaporated, and later on the water vapor dissociates into hydrogen and oxygen, and hydrogen being a light gas will escape to space. Okay. So, this is the effect, the positive feedback loop which caused the Venus temperature to rise so rapidly that the rocks started releasing carbon dioxide into the atmosphere. So, water triggered the runaway greenhouse effect in Venus. Okay. Now, this negative feedback effect is there, all of you know that as the temperature goes up, Earth loses more heat to the space, but if there is a lot of greenhouse gas in the atmosphere, this negative feedback will not be very effective. We will see how that will happen. Okay. So, Venus had first a wet runaway effect, that is water vapor evaporating from the ocean and increasing the water atmosphere and increasing temperature more and more. Okay. Once water vapor escaped from Venus after dissociation, then the dry runaway greenhouse effect came, where carbon dioxide came out of the rocks into the atmosphere. So, this went on for a longer period. So, the temperature went further and further up until it reached 720 degrees Kelvin. So, two runaway effects operated in Venus. One is wet in the beginning and dry later. This is assuming that Venus had an ocean. This is a hypothesis. We cannot yet prove that there was liquid water on Venus surface. Okay. This is a hypothesis. Now, Venus also had volcanoes which release carbon dioxide into the atmosphere. On Earth also volcanoes release carbon dioxide, but this ultimately goes back into the surface of the earth and beneath, because carbon dioxide is dissolved in rainfall, forms carbonic acid, which then reacts with calcium carbonate in the rocks and takes away the carbon dioxide into the ocean and ultimately into the rocks. Okay. So, in Earth's carbon cycle, the presence of water allows carbon dioxide to become carbonic acid and remove carbon dioxide from the atmosphere and put it into the ocean. Okay. Now, this could not happen in Venus when its temperature went up so high that water vapor completely escaped. So, this is what astronomers think that happened. Venus temperature went up. In Earth, it went up and reached this point close to triple point of water. This is the thermodynamic diagram of water vapor pressure versus temperature. All of you know this from your thermodynamics background. On Earth, the temperature was such that we were close to the triple point of water, and hence on Earth both ice, liquid water and water vapor coexisted together, and so we had the advantage of clouds which could reflect the sunlight. We had advantage of water vapor condensing and setting up a circulation in the Earth's atmosphere. All this is not there in Venus once the water vapor escaped. So, in Venus, this increasing temperature did not allow Venus to reach inside the liquid water phase diagram, but it went on in a way. Ultimately, there was photolysis of water, that is dissociation of water into hydrogen and oxygen, which did not happen on Earth. And so, water vapor decreased and carbon dioxide increased. So, in Venus, first water vapor boils out, then it causes a very high greenhouse effect in the atmosphere. After that, CO2 bakes out of the rocks. Okay. So, the question is, can something similar happen on Earth? The answer is, of course, it can happen, not immediately, but after a long time, because if the temperature of the Earth keeps going up due to our releasing carbon dioxide, then at some point the water vapor will keep increasing like in Venus, and very soon the temperature becomes so high that rocks will start releasing carbon dioxide. That of course will not happen in the immediate future, but the potential exists if we continue to allow carbon dioxide to increase in the atmosphere. So, now we understand that although Venus and Earth started with similar composition, similar diameter, similar amount of carbon, on Venus most of the carbon came into the atmosphere and it increased the greenhouse effect, while on Earth we were lucky that most of the carbon is stored safely as limestone in the sedimentary rocks of the Earth. Okay. It is locked up, but it can be released if the temperature goes up. So, that is a message that we get on Venus, that Earth right now is at a much cooler temperature, because most of the carbon dioxide on Earth is safely stored in the rocks and in the ocean, and only a small amount is in the carbon dioxide. So, runaway greenhouse effect applies to planets where greenhouse gases condenses at the tropopause or in the troposphere, and saturation vapor pressure links pressure and temperature of the atmosphere. Okay. So, for a fixed relative humidity, the mapping of temperature to optical depth sets an upper limit on the outgoing long wave radiation, okay, and that is determined by the physical and optical properties of the greenhouse gases. To explain this, let us go back to energy balance equation, which we started the course with. There is outgoing long wave radiation is balanced with absorption radiation. That is our balance, which you use in many examples. Now, if you use a simple Lewis model, which we discussed in great depth in the first few lectures in the course, and we neglect the absorption of solar radiation by the atmosphere for convenience, then OLR is 1 minus epsilon by 2 into sigma Ts to the power of 4. Okay. If we assume that emissivity of Venus is 1, which is reasonable because Venus contains a lot of carbon dioxide, then this will become 0.5 sigma Ts to the power of 4, and the highest value we will get for an albedo of, let us say, almost 0 will be around 288 Kelvin. So, albedo of 0.3 is 288 Kelvin. Okay. So, this shows that this simple model of Lewis is not valid for Venus. Why is it not valid? Because Venus atmosphere is very thick today, 100 times thicker than the Earth, and so we cannot replace the entire atmosphere with one layer at one temperature, which is what we did for Earth and which was adequate for a simple model of the Earth's atmosphere. For Venus, we had to adopt a very different approach, where you had to allow temperature to vary with height. Okay. That makes the radiative transfer calculation very complicated, which we will not talk about in this course. But if any of you are interested, there is an NPTEL course on thermal radiation heat transfer, which in which I have given lectures, where we derive the equation for radiative equilibrium, where we allow the temperature of the atmosphere to change with height. Okay. So, if you do that, the OLR value for such a atmosphere in radiative equilibrium will be sigma Ts to the power of 4 divided by 1 plus 0.75 kappa 0. Kappa 0 is the optical depth, the total optical depth of the entire atmosphere. Okay. That is nothing but the vertical integral of the mass absorption coefficient, which we discussed earlier in the course, multiplied by the density of the vapor and the vertical level dz, and that you integrate from surface to the top of the atmosphere. Okay. Now, the mass absorption coefficient of the vapor in the atmosphere depends on the vapor pressure, which we assume if it is saturated, it is a saturated vapor pressure which can be obtained from the Clausius-Clapeyron equation in thermodynamics. So, the optical depth, the total surface to top of the atmosphere, is controlled by the mass absorption coefficient and the saturation vapor pressure of that greenhouse gas, which depends on temperature. So, we see that if the vapor in the atmosphere of Venus is saturated, then its amount will keep increasing with temperature following the Clausius-Clapeyron equation. Okay. So, that is unavoidable, determined by the laws of thermodynamics. Okay. So, if the atmosphere of Venus is saturated with vapor, then the optical depth will increase exponentially with surface temperature, and that is what causes the runaway greenhouse. The runaway greenhouse is occurring because Venus from the beginning had either a saturated water vapor, and after it evaporated it had saturated carbon dioxide. Okay. So, initially it was a wet greenhouse effect, later on it was a dry greenhouse effect. So, this is the key part, and this equation is very important to understand that the right hand side is controlled by albedo of Venus, which we can assume to be roughly constant because the cloud is always covering Venus. So, as the temperature goes up, copper 0 goes on increasing, so OLR goes on decreasing, and if OLR goes on decreasing, but the right hand side remains constant, we saw that there is an imbalance between the radiation emitted and radiation absorbed. As the temperature goes up, the radiation emitted goes down, while the absorbed solar is not changing. So, this will force the temperature of the planet to go up, there is no alternative. Okay. That is what happened in Venus. Okay. This can be shown graphically if there is no saturated vapor or no greenhouse gas atmosphere. OLR goes as sigma T to the power of 4, all of you know that, assuming the surface of Venus is black. But suppose the vapor is saturated, relative humidity is 100%, then the OLR will not go on increasing, will become completely flat, because as the temperature goes up and the water vapor increases, it traps more and more of the surface radiation. Very soon the OLR is independent of temperature. So, that is the key point. There comes a point where OLR is independent temperature, but the absorbed solar may not be depending on temperature. So, this quantity is higher than this quantity. So, planet becomes unstable and it goes on a runaway greenhouse effect until some change in the absorbed solar brings the right hand side and left hand side into balance. So, this is what you must understand. This is the nature of the greenhouse effect, that the planet's ability to emit radiation becomes less and less as the greenhouse gas goes up, while the absorbed solar does not change much. Okay. So, this is what causes runaway greenhouse effect. This is shown in another graph here, showing the outgoing long wave radiation in 3 cases. One, CO2 is 100 ppm, RH of water vapor is 10%. Okay, then there is no problem, it keeps increasing. But if the CO2 is 100 ppm and RH goes to 70%, then you can see that the OLR reaches asymptote. It does not go beyond, in this case, 320 watts per meter squared. Okay. And if you increase the carbon dioxide concentration to 0.2 bar and water vapor humidity is 70%, it is even less. So, the key point is, depending on the properties of the greenhouse gas which is saturated in the atmosphere, there is a limit called the Kobayashi-Ingersoll limit, which tells you what is the maximum amount of long wave radiation that atmosphere can emit to space. So, if the absorbed solar is larger than that, then the atmosphere temperature will go on decreasing until some balance is achieved. Now, this is a simulation done by Bullock and Greenspoon, taking the Earth's atmosphere and increasing the amount of carbon dioxide, and you can see that temperature keeps going up to 700 Kelvin. Okay. As the temperature goes up, carbon dioxide goes up, and that is the carbon in the rocks all come out, and the temperature goes on increasing. Okay. So, this is possible on Earth also, provided carbon dioxide comes out of the rocks. So, the key point is that if there is sufficient amount of saturated vapor in the atmosphere, it will prevent the atmosphere from cooling to space. So, the negative feedback, which we call the Planck feedback, is not there. So, that is why the temperature goes on increasing. Now, in contrast to the Earth, the composition of Venus atmosphere is controlled by chemical reaction on the planet's surface. On Earth, the chemical reaction is not very rapid because temperature of Earth is quite low, 288 Kelvin. While the Venus temperature is high, the chemical reaction is very, very rapid in Venus. Okay? So, the surface temperature depends upon how much of the gas escapes from the rocks into the atmosphere. Okay? So, composition is controlled by chemical reaction at the surface temperature of Venus. Okay? On Earth is much smaller because of lower temperature. Here is an example how the albedo of Venus, which contains sulfuric acid, haze particles and clouds, how it decreases with amount of sulfur dioxide in Venus. Okay? You can see that as sulfur dioxide increases, more clouds form, more aerosols are there. So, there is a chemical albedo feedback. Okay? On Earth we had ice albedo feedback, on Venus we have a chemical albedo feedback. So, in Venus, because of its high temperature, the atmospheric composition controls the temperature of Venus, and the temperature of Venus controls the composition. So, this is a interacting system. As the temperature goes up, the atmosphere's chemical composition changes, SO2 and CO2 change, and as they change the atmospheric temperature. So, here you are talking about both albedo change due to sulfur dioxide and greenhouse effect change due to carbon dioxide. So, in Venus, the energy balance is more complicated. There is volcanic outgassing like on Earth, there is surface reaction, chemical reaction going on, which changes the composition of the Earth, and that affects the radiative heat transfer in Venus, and there are clouds in Venus which trap radiation, and so all these are controlling the radiative convective equilibrium at the Venus atmosphere. Now, Bullock and Grinspoon talk about the kinds of reactions that go on in the Venus surface. One is calcium carbonate reacting with silicon dioxide produces calcium silicate and carbon dioxide. Okay? And there is also a reaction between sulfur dioxide, calcium carbonate, which produces calcium sulfate and carbon monoxide. Okay? So, these reactions going on along with also pyrite and magnetite, all these reactions are going on, all of them depend on temperature. As the temperature goes up, all these reactions go much more rapidly and they release more carbon dioxide. Okay? So, this particular reaction they have discussed, the carbonate silicate reaction, creates calcium carbonate when the temperature is below 300 degrees centigrade. But if the temperature goes above 300, the reaction goes the other way around and it releases carbon dioxide. So, all of you know the reaction can go both ways, chemical reaction. Which way it goes depends on temperature. At low temperature, the reaction goes in the forward direction. At the high temperature, the same reaction goes in the backward direction. So, once the Venus temperature reaches above 300 due to the water vapor greenhouse effect, this reaction will take over and release more carbon dioxide. Okay? So, that is the point you have to remember about Venus. It started with the water vapor as a main source, the wet greenhouse, and then it went on to the dry greenhouse, which is this reaction. Okay. Now, you can calculate this reaction rate releasing carbon dioxide and what will be its partial pressure. Okay. So, this is the relationship between carbon dioxide and temperature in Venus due to a chemical reaction. This is governed by the Arrhenius chemical reaction equation. Okay. This is similar to the Clausius-Clapeyron equation for water vapor, but this is occurring at higher temperature. So, this particular equation says that at 92 bar surface pressure at a temperature 742, we reach a chemical equilibrium. Okay. It's a very interesting result, because the observed pressure in Venus is around 92 bar, the observed temperature around 750 bar. This is the equilibrium condition according to the Arrhenius equation. Okay. So, this can be shown graphically in a very nice way. In Venus, the final temperature and final pressure which is reached, okay, is governed by chemical equilibrium and radiative equilibrium, okay, radiative convective equilibrium. Okay. And these two meet at 720 Kelvin. So, the present temperature of Venus is 720 Kelvin because at that temperature the radiative convective equilibrium and the mineral equilibrium due to chemical reaction that release carbon dioxide, they both reach a condition where the temperature and pressure ensures that chemical reactions are in steady state and the energy balance in steady state. Both must be in steady state to have the final steady state Venus pressure and temperature. So, this is an important point you have to remember, that the present Venus temperature of 720 and pressure of 100 bar is because of the combination of chemical equilibrium and radiative convective equilibrium. Now, the conclusion is Earth and Venus started similar way. In Earth, carbon is safely buried in sediments and in ocean, avoiding runaway greenhouse effect. Venus, the CO2 built up in the atmosphere and it reached very high temperature. So, if you want to prevent runaway greenhouse on Earth, you need to make sure we don't go on burning fossil fuels forever. If we did that, then there is a possibility of a runaway greenhouse effect on Earth also, not in the next 100 years, but over a long period. Okay. So, Earth is continuously removing carbon dioxide due to the CO2 cycle on Earth through vegetation and carbon dioxide. That is not happening on Venus because Venus has no ocean now. Okay. And this hydrolysis is what controls CO2 on Earth. Okay. And chemical weathering will occur on Earth only at much higher temperature. So, on Earth, runaway greenhouse can occur if there is no ice and cloud. If you go on allowing temperature to go up, all the ice melts and cloud all move away, then that can happen. One more way is, sun's intensity is continuously increasing as a star. If it reaches very high values a billion years from now, then Earth will also have a runaway greenhouse. Okay. So, global warming could be one which can lead Earth to a very hot future. Okay. So, we end by saying that there is no likelihood that Earth will actually come to resemble Venus, but Venus serves both as a warning that a major environmental effects can flow from seemingly small causes and as a test bed for the models we develop on Earth. This is a comment made by Hunter a long time back, more than 30 years ago. It tells you that we may not reach the condition of Venus, but Venus is a warning that such a thing could happen if you are somewhat careless. So, I end this lecture on that note, and our last lecture will be a wrap up on what we learned in this course. Thank you.